morning, everybody. Thank you for making it here at this early time in the morning. I'd like to talk about our work on collaborative text editing. This is work I did together with my collaborator, Joseph Gentle. Seth is based in Australia, and so it was quite a long way for him to come here, so I'm presenting the work on his behalf. We were very happy to receive the Best Artifact Award for this software artifact yesterday. I should emphasize that the artifact is entirely Seth's work, so I take no credit for that at all. So thank you to him for doing all the great work on that. Okay, so collaborative text editing is something you're probably familiar with as a user of tools like Google Docs, for example, or Overleaf. And those products use a family of algorithms called operational transformation. Operational transformation has been around for a long time. Research on it started in the late 1980s and continued over quite an extended period of time. There were a bunch of problems with OT algorithms, and so therefore, later on then in the early 2000s, an alternative family of algorithms came up that can also be used for collaborative text editing. And this family is called conflict-free replicated data types, or CRDTs. CRDTs are less used currently in sort of mainstream production software that you're probably familiar with, but they are starting to come into use in tools like, for example, Jupyter Lab added real-time collaboration based on the YJS CRDT library, Evernote, a note-taking app, and various others are now built on CRDTs. So both of these are used in practice. And the core problem that these collaborative text editing algorithms need to handle is merging concurrent edits to a text document. And so let's say you have two users, the red user and the blue user. They both start off with the same document that says hello exclamation mark. And let's say that each user edits the document on their own computer. Now, you want each user's own edits to be immediately applied to their own copy of the document without waiting for a network round trip, because the software would be painfully slow to use if you had to wait for network round trip on every keystroke. And so therefore, since you immediately apply to the local copy of the document, that means you can get temporary divergence of the users. So maybe one user types the word world before the exclamation mark, and concurrently on a different device, the blue user types a smiley face after the exclamation mark. And then network communication happens, and the algorithm needs to somehow merge those changes together into such a way that preserves the input from all of the users. And so in this case, a sensible merged result would be hello world exclamation mark smiley face. So the way that operational transformation performs this is it records every keystroke you make in terms of an operation that describes at which index of the document a character was inserted or deleted, or perhaps a sequence of characters. And so here in this simplified example, we start off with a document that says just HELO, and then let's say the blue user on the left wants to insert a second letter L at index 3, and concurrently the red user on the right wants to insert an exclamation mark at index 4. And those result then in diverged document states, and now we need to merge them back together again. OT does this by calling a transformation function. This transformation function takes as input two concurrent operations and returns two transformed operations, such that if you apply, for example, the left original operation and the right transformed operation, you get the same result as if you apply first the right input operation and the left transformed operation. So in this case, the transformed operation of inserting L at index 3 is just exactly the same. It's still insert L at index 3, but the transformed version of the insertion of the exclamation mark, well, it has to put its insertion at index 5 now, because if it put the insertion at index 4, then the exclamation mark would end up in the wrong place. And so this way now, the two users can merge their states back together again by applying the transformed version of the other user's operation. So this is the case where you have one operation concurrent with one other operation. In general, the users could diverge by more than one operation. So let's say the blue user on the left inserts A and then B, and then concurrently the user on the right inserts X and then Y. And then a more complicated transformation procedure is necessary where we take pairwise operations, get some transformed operations from those, transform the transformed operations again, blah, 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 blah. So all the details are a little bit fiddly. And you can see in just from this kind of lattice structure that you end up with here, you can end up with all of the users ending up with a converged state again. But if you have n operations on the left-hand path and also n operations on the right-hand path, there will be a quadratic size lattice here that you have to go through. So there's a quadratic number of calls to the transformation function you need to make. And so therefore, as these users have diverged by a substantial amount, this merging process just gets extremely slow. This quadratic algorithm is really slow. Now, in the typical real-time collaboration use case, this doesn't really happen because the users only diverge by 2 or 3 keystrokes with a typical network latency, and therefore this is fine to have a quadratic algorithm there if n is small enough. But if you want to allow users to edit a document while they're offline, for example, then you might accumulate substantial amounts of divergence that you then have to merge when the users come back online again. And offline working is a pretty useful feature to have. Moreover, maybe you want to support not just real-time collaboration, but something, a kind of workflow that is more like pull requests or so, where you go off on a branch, make a bunch of changes, and then sometime later decide whether to merge with somebody else's branch. That then means, again, you get substantial amounts of divergence. And so if you're wondering why does Google Docs and Overleaf not support pull requests, it's exactly for this reason that it would be dog slow, because they're running a quadratic or even worse algorithm here. And they're sort of different points on the spectrum of how asynchronous you want the collaboration to be. So we did some experiments, and we implemented an OT algorithm in a way that is comparable implementation-wise with our Egg Walker implementation. Egg Walker is our algorithm in this paper. And you can see here that we have a couple of different editing traces. These are real editing traces of real text documents that we used as benchmarking data sets. And the 3 green traces, S1 to S3, they are sequential. They have no concurrency, no merging. It's just one user or multiple users taking turns, but no concurrency. And so both OT and Egg Walker are very fast to process these traces in single-digit milliseconds. But if you look at some of the other traces that have a lot of divergence and then big merges, then putting this thing on a log scale, you can see that OT takes over an hour to process one of these traces, whereas Egg Walker processes the same trace in 23 milliseconds. This is a performance improvement of 150,000 times. The trace in this case is actually derived from the make file of the Git repository for Git itself. So it's a real file that real users, real humans are working on, and it just shows that these branching and merging patterns can get extremely expensive to execute if you do it with OT. Okay, so let's look at the competition, CRDTs. CRDTs work totally differently. They don't transform operations. Instead, the key idea there is that we give each character a unique immutable ID, and even as characters change their position in the text, that ID stays the same, and that gives us a stable anchor. There are different ways how you can construct these IDs. So for the sake of simplicity, I'm just going to represent them as rational numbers for now. In practice, they would be things like a path through a tree or stuff like that. And you can think of these numbers as simply indicating positions in the text, where the start of the text is 0, the end of the text is 1, and fractional numbers just represent some position ordered by number. And so now if you have HELO, and you want to insert a letter L between the first letter L and the O, and if L has a value of 0.6 and the O 0.8, you could just pick a number somewhere in between, say 0.7, and that then tells everyone where that character should go. Now, if you have multiple users concurrently inserting at the same position, they might end up picking the same number. And so therefore, in order to tie break, in that case, you would also need to tag each character with the ID of the device that inserted it. Some kind of unique device ID in combination with the number will do. And so now the merging is really simple. We just have, you can think of it as this set of tuples where each character is tagged with a number and the ID of the device that inserted it, which is A in these examples. And now if you want to apply some edits, such as inserting L at position 0.7, inserting the exclamation mark at 0.9, it's easy. We just take a set union and you get a merged document. Very straightforward. The trouble with this is now you have a lot of additional metadata that you have to carry around because you have these numbers. You can't just use floating point numbers because you would run out of precision, so you need to use arbitrary precision numbers representation for this. The device IDs will be a bunch of bytes as well. And so there's quite a lot of overhead for every single character. And all of this overhead, unfortunately, then uses a lot of memory. And it also means that loading a document off disk is slow. There are nice compression schemes that allow us to use quite compact file formats for CRDTs on disk, but as you load them into memory in order to make the document editable, you have to expand them into these quite large in-memory data structures. And this really shows up in the evaluation as well. So if we look here at the time that it takes us to load a document from disk into memory, in Egg-Walker, it's extremely fast. It's less than a millisecond on all of our traces. Whereas if we combine this, if we compare this to two production-grade CRDT libraries, AutoMerge and YJS, you can see that they take at least tens of milliseconds, if not hundreds of milliseconds, if not several seconds. So in the case of AutoMerge, Egg-Walker is 4 to 5 orders of magnitude faster to load a document off disk, just because it doesn't have to deal with all of this additional metadata overhead. In the case of YJS, the difference is less extreme, but it's still quite a solid multiple performance improvement. And so that's the time. If we look at the actual memory consumption of these algorithms, what we did here in our evaluation is to actually break down Egg-Walker in differentiating between peak memory use and steady-state memory use. The peak memory use is what happens only while Egg-Walker is in the process of merging multiple branches or merging updates from a remote user. And then as soon as that merging process is completed, Egg-Walker is able to free a bunch of memory. And while a document is just being edited locally by a user, what applies is this steady-state memory consumption. So most of the time we're in this steady-state memory consumption, and just occasionally, if there's a big merge, then we go to this peak memory consumption shown here. Whereas in YJS and AutoMerge, there isn't really this distinction between peak and steady-state. They sort of require more or less constant memory use all of the time, and therefore we haven't split it up this way for those libraries. So if we compare YJS to Egg-Walker, it depends a bit on the trace. So for some traces, Egg-Walker at peak uses 2 to 4 times less memory than YJS. But there are also some traces in which Egg-Walker takes 2 to 4 times more memory. But this is only during the peak, only during a large merge. And this is actually the only place in which Egg-Walker does not beat the state of the art. In all other places, there's quite a significant performance improvement again. So if we compare the steady-state memory use of Egg-Walker, then we're somewhere between 20 and 400 times lower memory use than YJS. And if we compare it to AutoMerge, we're better. Even the peak memory use of Egg-Walker is significantly lower than the steady-state memory use of AutoMerge. And comparing the steady-state use of Egg-Walker to AutoMerge, it's again quite dramatic. And in case you think I'm being particularly harsh on AutoMerge here, AutoMerge is a project I started myself. So I'm really comparing against our own prior work here. There is work happening in YJS and AutoMerge to try and bring these memory usage numbers down, but this is the state as of the currently released versions of the software. So to summarize this, we have these two existing families of collaborative editing algorithms, OT and CRDTs. OT are very good for speed of loading a document from disk. In that regard, OT and Egg-Walker are basically the same, and the same goes for memory use. Both OT and Egg-Walker are very efficient, and CRDTs are really bad in terms of the loading performance and the memory use. However, OT, as I mentioned, has this downside of being really slow to merge, especially if the users have diverged by a substantial amount, whereas CRDTs are fast, and Egg-Walker inherits the property here that it's also fast in order to perform those merges. And the last criterion on which I want to compare them is whether these algorithms are decentralized or require a central server. So in the case of CRDTs and Egg-Walker, they are decentralized. So it means you can run them over a peer-to-peer network if you want. You don't have to. You can use a central server if you want. You can use a federation of multiple servers if you want. It just doesn't matter what sort of network topology you want to use. In the case of OT, there are algorithms, OT algorithms, that support peer-to-peer use, but the ones that are actually used in practical software are, as far as I know, all centralized. So they assume that there's a single server that all of the communication goes via, and they can't be used in peer-to-peer settings. So we have these two existing families of algorithms. I don't really have time at all to tell you about how the egg-Walker algorithm works. You can read the paper for that. But the core idea is really that we've tried to take the best of both of these existing worlds and bring it together in a single algorithm. So from operational transformation, we've taken the fact that there's no per character metadata overhead, which just massively saves on memory use and load times. But from CRDTs, we've taken the fact that it doesn't have to do this n by n matrix of transformations, and so therefore doing large merges is much faster. And we've also taken from CRDTs the property that it works in a decentralized way. Internally, egg-Walker really has characteristics of both, so you can regard it as an OT algorithm or as a CRDT algorithm. It's really both. And so in some ways, we've also now just removed the distinction between these two families of algorithm, that you could now consider them both one. All of the details are in the paper. You can find the artifact that includes all of the code, all of the data and experiments. And there are two implementations of this, a Rust implementation, which was the basis of the evaluation data that I showed you. The Rust implementation is optimized for performance. But there's also a TypeScript implementation that has the same behavior, but which is optimized for readability of the algorithm and not for performance. And so therefore, if you're trying to understand the algorithm, then actually looking at the TypeScript implementation is a good idea. The Rust implementation has a lot more complexity because it uses fancy B trees and stuff like that in order to actually achieve its performance goals. But this is what we have anyway. So thank you very much, and I'm happy to take questions.